In the language of the universe, collapse is not simply an ending. It is a beginning. When a star burns through the last of its fuel, it implodes, collapsing under its own gravity. In that moment of destruction, the furnace ignites elements that will one day shape planets, oceans, and living beings. Out of collapse, life is written. When a black hole forms, space itself buckles inward, folding reality into a darkness from which not even light can escape. Yet these same black holes sculpt galaxies, driving their evolution, stirring gas, and guiding the growth of stars. Out of collapse, order emerges, and when the universe itself was young, there was no calm unfolding, no gentle awakening. Instead, perfection shattered. A primordial symmetry gave way. Energy collapsed into matter, forces broke apart, and from the uniform silence came the diversity of everything: quarks, electrons, galaxies, and minds, able to question their own origins. Collapse is paradox. It is annihilation, yet also creation. It tears apart, and yet from that tearing new forms rise. It is fragility and inevitability bound together, the quiet signature of a cosmos that does not remain still. But what was the first collapse, the one that birthed everything we know? Was it the fall of a false vacuum, the sudden rupture of space-time from nothingness, the collapse of symmetry that could not hold? This is not merely the story of destruction. It is the story of a universe that could only come to be by breaking itself, the story of fragility as foundation, the story of the collapse that created everything we know. Long before the language of science, collapse lived in myth. Ancient cultures told stories of worlds born from chaos, of heavens falling into order, of gods who tore the sky apart to shape the earth. In Mesopotamia, the Enuma Elish spoke of creation, from the sundered body of a primordial sea goddess. In Greece, Hesiod described the cosmos emerging from chaos, the yawning void. In India, the Rig Veda imagined a time when there was neither death nor immortality, only an undivided whole, waiting to break. Collapse was remembered not as destruction, but as a force that made form possible. Philosophers, too, wrestled with the paradox. Plato spoke of the cosmos as a fragile order imposed upon disorder. Aristotle denied the existence of a vacuum, insisting nature abhorred emptiness, as if collapse itself was forbidden. Yet in other traditions, among Chinese cosmologies, for example, cycles of destruction and rebirth were inseparable, yin and yang eternally collapsing into and out of one another. With the birth of classical science, collapse was recast. For Newton, the cosmos was a vast clockwork. Stars and planets traced paths according to universal laws of motion and gravity. Space itself was unchanging, an infinite stage upon which matter moved. Collapse was reduced to a minor detail. Apple falling, a stone descending, a comet pulled into the sun. Reality was eternal, stable, and secure. The universe did not begin and would not end, but Einstein shattered that comfort. In his theory of general relativity, space and time were no longer a stage but a fabric, pliable and fragile, warped by energy and mass. Collapse was now written into the structure of space-time itself. A star that grew too heavy would no longer be able to resist its own weight. It would not simply burn out, it would implode, curving space-time into something unprecedented. In 1939, J. Robert Oppenheimer and Hartland Snyder calculated the fate of such a star. Their equations revealed an end so absolute it seemed almost impossible an object collapsing beyond recovery, shrinking without limit, leaving behind only a region where spacetime itself was cut off. This was the first glimpse of the black hole, a collapse so profound it erased place and time. Astronomers soon saw collapse written across the heavens. Stars ended not quietly but in explosions, supernova, moments when the core collapses inwards and rebounds, tearing the star apart, in brilliance that outshines galaxies. In that collapse, heavier elements were forged: carbon, oxygen, iron, gold. Every atom in every human body was once formed in such a death. Collapse was no longer myth. It was the alchemy of reality. But collapse did not only belong to stars. It appeared on a cosmic scale. In the 1920s, Edwin Hubble peered through the Great Hooker telescope at Mount Wilson and saw galaxies beyond our own. They were not fixed, not static. They were receding. The farther away they were, the faster they fled. The universe itself was expanding. If it was expanding now, then long ago it must have been smaller, denser, hotter, until everything was collapsed into a single unthinkable origin. The idea of the Big Bang was born, a universe emerging not from eternity, but from an unfathomable collapse of nothing into something. The idea remained controversial. Many resisted it, preferring a steady-state cosmos with no beginning. But evidence grew. In the 1940s, George Gamow, Ralph Alfder, and Robert Herman predicted that if the universe had once been a collapsing fireball, a faint glow should still remain, stretched into microwaves as the cosmos expanded. In 1965, two engineers at Bell Labs, Arno Penzias and Robert Wilson, stumbled upon a persistent hum in their radio antenna. They tried everything to eliminate it, even removing pigeon droppings from the equipment. Yet the noise remained uniform, from every direction. It was not interference. It was the afterglow of creation itself, the cosmic microwave background, the fossil light of a universe born from collapse. With that discovery, collapse was written into the sky. No longer myth, no longer speculation, but measurable fact. The universe was not eternal and unchanging. It was dynamic, fragile, the child of violent beginnings. And beneath these discoveries lay an even deeper realization. Collapse was not an isolated event, not a rare catastrophe, but the rule by which the universe advanced. Stars lived and died through collapse. Galaxies took shape when clouds of gas collapsed under gravity. Heavy elements were released only when stellar cores imploded. Even the universe itself bore scars of collapses more fundamental still, moments when symmetry itself broke, and new laws of physics emerged, from myth to philosophy, from Newton to Einstein, from Hubble to Penzias and Wilson. The narrative had shifted. Collapse was not destruction, but creation's engine. The universe was not a clockwork running eternally. It was a story of fragility, of shattering, of beginnings written through endings. And yet, as scientists looked closer, one question rose above all others. If collapse had shaped everything we see, could it also destroy everything we know? Collapse had long been seen as an end, the extinguishing of stars, the crushing of matter, the fall of fragile things. But as the 20th century unfolded, science revealed something more unsettling. Collapse was not the exception, but the rule. It was everywhere, shaping reality at every scale. The first shock came from the stars. For centuries, they had been imagined as eternal fires, steady and unyielding. Yet observation betrayed their fragility. Telescopes revealed stars that swelled and dimmed, novas that erupted suddenly into brilliance, supernova that lit the sky with the fury of a billion suns. These explosions were not mere accidents, they were collapse written in light. When a star exhausted its fuel, its core fell inward, crushing under its own gravity. Some rebounded, creating titanic detonations that seeded space with new elements. Others collapsed so completely that nothing remained but a neutron star, a sphere of unimaginable density. And still others disappeared into something stranger. Black holes, where collapse did not stop at all. This was not destruction, it was transformation. Out of collapse came iron, carbon, oxygen, the very ingredients of life. Collapse made the universe habitable, yet the same process also threatened everything with annihilation. A black hole, once born, devoured without mercy. It bent light, warped time, erased information. Collapse was creative, but it was also absolute. The next shock came not from the stars, but from the laws of physics themselves. In the earliest universe, forces had once been united, a single symmetry without distinction. But as the cosmos cooled, that symmetry collapsed. The electro-weak force split into the electromagnetic and weak nuclear forces. The strong nuclear force separated. Before that, with each collapse, the universe gained structure. Particles acquired new properties, interactions emerged, matter as we know it became possible. Without these broken symmetries, the universe would have remained featureless, empty, sterile, and yet this truth was terrifying. If collapse had shaped physics once, could it happen again? Could the symmetries of our universe break further, tearing away the foundations of existence? The universe began to look less like a stable edifice and more like a precarious arrangement, balanced upon fragile laws that might collapse anew. The most profound shock of all emerged in the late 20th century. Inflation theory, proposed in the 1980s, suggested that in its earliest instant the universe expanded faster than light itself. This sudden burst was triggered, physicists proposed, by the collapse of a primordial field. As that field decayed, it released energy, blowing spacetime outward in a frenzy of creation. From collapse came expansion, the cosmos we inhabit. Every galaxy, every star, was born of a field falling into a lower state. Collapse, once again, as Genesis. But inflation carried a darker implication. If one collapse could start our universe, why not others? What if collapse is still occurring elsewhere, birthing countless universes beyond our reach? The idea of the multiverse was born, not from speculation, but from collapse itself. Even in laboratories, collapse defied comfort. Quantum mechanics revealed that particles exist not as fixed entities, but as probabilities spread across possibilities. Only when observed did they collapse into definite states. Reality itself seemed to depend on collapse, an unavoidable narrowing, from possibility to fact. Each measurement, each moment of existence, was a collapse from infinity into one outcome. Then came the most chilling possibility. The Higgs field, discovered in 2012, gave mass to particles, anchoring reality. But calculations suggested that the Higgs vacuum, the state in which this field exists, may not be perfectly stable. It may only be metastable, balanced precariously on a false floor. If so, a deeper vacuum state might exist. And if the Higgs field were ever to collapse into that lower energy, the result would be catastrophic. Space itself would be rewritten. Atoms would dissolve. Physics would be annihilated. The universe would end, not with fire or ice, but with collapse. This is the nightmare of false vacuum decay. It would occur without warning, a bubble of collapse expanding at the speed of light, erasing everything in its path. No escape, no defense. A collapse that does not create, but only destroys. Thus collapse revealed itself as both miracle and menace. Without it, there would be no galaxies, no stars, no life. But because of it, there may also be no permanence. No safety, no eternity. It is the paradox at the heart of physics. Collapse is the architect of existence, and the shadow of its end. The shock was not only scientific, but philosophical. For centuries, humans had sought permanence in the heavens, imagining stars as eternal and the cosmos as fixed. Now science insisted otherwise. Reality is fragile, contingent, unstable. Its very laws were born from collapse and may collapse. Again, the realization was almost unbearable. Permanence is an illusion. The universe is not built upon eternal foundations, but upon fractures. Collapse does not lurk at the edges of existence. It is woven into its heart, and so the story deepens. The question is no longer whether collapse created what we know, but whether collapse may yet unmake it. The shocks of discovery had revealed collapse as a universal principle, but shock alone was not enough. Science thrives not only on revelation, but on measurement, on evidence gathered with relentless precision. If collapse shaped the cosmos, then its fingerprints must be written somewhere in the stars, in the sky, in the subatomic heart of matter. And so humanity began its deeper investigation. The first map of collapse lay in the faintest glow of the cosmos itself. In 1965, Arno Penzias and Robert Wilson, while calibrating a radio antenna in New Jersey, stumbled upon a whisper of microwave radiation. It came from every direction, unyielding, impossible to erase. What they had uncovered was the cosmic microwave. Background, the fossil light of the early universe, the afterglow of a collapse 15 billion years past. Later missions, COBE, WMAP, and most recently Planck, traced this radiation with astonishing clarity. The microwave sky was not uniform. It bore tiny fluctuations, minute ripples in temperature, no more than 1 part in 100,000. Those ripples were seeds, imprints of collapse in the infant cosmos. Quantum fluctuations, magnified by inflation, collapsed into density variations that gravity would amplify into galaxies, clusters, and the great cosmic web. From the afterglow, collapse had spoken. The universe we see today, the very distribution of stars, emerged from the smallest collapses of probability. The random became the real. Deeper investigation turned next to the stars themselves. Telescopes revealed that collapse was not an event of the distant past alone, but a process continuing all around. Astronomers watched supernova flare across galaxies, brief outbursts marking the collapse of massive stars. From the analysis of their spectra came proof of heavy elements forged in collapse, iron at stellar hearts, gold and uranium from neutron star collisions. The cosmos was a recycling ground, collapse the furnace in which diversity of matter was made. To trace collapse was to trace the very origin of the periodic table. The tools of astronomy reached further, mapping collapse not only in starlight but in structure. The Sloan Digital Sky Survey charted millions of galaxies, revealing that they were not scattered randomly but arranged in filaments and walls. A cosmic web stretched across billions of light years. These patterns bore the memory of primordial collapse. Embedded in this web were baryon acoustic oscillations, the frozen echoes of sound waves that rippled through the hot plasma of the early universe, waves that collapsed into the scaffolding of cosmic structure, but collapse spoke to in the trembling of space-time itself. In 2015, the Laser Interferometer Gravitational Wave Observatory LIGO detected the first gravitational waves, ripples in space-time from the collapse of two black holes spiraling into merger. This was collapse made audible, space-time ringing, like a drum as matter folded into nothingness. Since then, dozens of detections have followed. Black hole mergers, neutron star collisions, echoes of collapse reaching us across billions of years. For the first time, humanity could hear the universe collapsing, and yet, even as telescopes and detectors revealed collapse on cosmic scales, laboratories probed it on the smallest. In 2012, the Large Hadron Collider confirmed the Higgs boson, a particle born of a collapsed field. The Higgs field itself is evidence of symmetry breaking, a collapse that once gave mass to all particles. Without that collapse, there would be no atoms, no chemistry, no structure. It was as if collapse had written itself into the laws of existence. But with that discovery came unease. Calculations suggested that the Higgs vacuum might not be perfectly stable. The very field that holds reality together may one day collapse into a lower state. Particle accelerators had not only revealed collapse, they had revealed that collapse may still be waiting. Deeper still, collapse was traced in the quantum fabric. Electrons orbiting hydrogen atoms do not move in neat paths. Their positions are probabilities. When measured, those probabilities collapse into outcomes. The Lamb shift, a tiny change in hydrogen's spectral lines, revealed the subtle influence of vacuum fluctuations, particles appearing and vanishing, fields collapsing and re-emerging in restless motion. Even in the quietest atom, collapse shaped reality. Investigations extended to black holes, where collapse became absolute. Stephen Hawking proposed that even at their horizons, collapse was not silent. Quantum fluctuations near the boundary would led to Hawking radiation, a faint glow that slowly evaporates black holes. If true, even collapse is not final. The darkest objects in the cosmos would one day dissolve into light. Yet the paradox remained. What becomes of the information swallowed in collapse? Does it vanish, violating the laws of physics, or does the universe preserve it in ways beyond our comprehension? Collapse had become not only a phenomenon to observe, but a riddle to endure. Simulations, too, entered the investigation. With supercomputers, physicists modeled universes filled with particles and forces, testing how collapse shaped them. From the collapse of quantum fluctuations into galaxies, to the collapse of stars into black holes, to the possible collapse of the Higgs vacuum, simulations gave form to what observation alone could not reach. Collapse was shown to be universal from the smallest quanta to the largest clusters. Even the detection of neutron star mergers deepened the mystery. When LIGO and Virgo observed one in 2017, telescopes across the world watched. Light and waves combined to reveal an astonishing fact. Gold, platinum, and other heavy elements were forged in that collapse. Human jewelry, technology, even the metals that shape civilizations, all were born in the collapse of stars. The deeper the investigation, the clearer the paradox became. Collapse was everywhere, creative and destructive, past and present. The fingerprints of collapse were etched in the background radiation of the universe, in the distribution of galaxies, in the whispers of gravitational waves, in the atoms of our bodies. And yet, every discovery also deepened unease. If collapse is universal, then permanence is an illusion. If collapse created everything, then collapse may also unmake it. In the silence of detectors, in the data of telescopes, in the equations of physicists, one truth emerged. Collapse is not an event. It is the rhythm of the cosmos, the pulse of creation itself. But with each investigation, the mystery only widened. For collapse had not revealed its final face. Collapse had revealed itself as the secret architect of creation. It shaped galaxies, forged elements, seeded structure from the tiniest tremors of the early cosmos. Yet in its revelations lay something darker. The more deeply collapse was traced, the more its shadows grew. For collapse was not only the beginning, it was also a promise, or perhaps a threat, that the universe itself remains fragile, suspended between creation and annihilation. The first deepening came with the recognition that collapse is not finished. Stars still collapse into black. Holes, galaxies still collide. Spacetime still trembles with waves of matter falling inward. These were not ancient events frozen in history. They were ongoing. The night sky itself is alive with collapse, unfolding in silence across unimaginable scales. The realization shifted collapse from past to present, and then, inevitably, to the future. In the late 20th century, astronomers expected that cosmic expansion would eventually slow. Gravity, the great puller, would resist the outward rush of galaxies. Some imagined the universe collapsing back into a big crunch, returning all matter and energy to a final inferno. But in 1998, a different fate appeared. Observations of distant supernova revealed that the expansion was not slowing, but accelerating. Something later called dark energy was pushing the cosmos outward, faster and faster. The implications were staggering. If this acceleration continues, collapse will vanish from the large-scale future. Galaxies beyond our local group will slip over the horizon, unreachable forever. Collapse will persist only in isolated pockets, stars folding into remnants, black holes consuming matter. But the grand cosmic collapse, the gravitational weaving of the universe into vast structures, will halt. Instead of collapse gathering the cosmos together, expansion will tear it apart. This paradox sharpened the mystery. Collapse creates structure, but expansion unravels it. Which force will rule in the end? Worse still, the Higgs field whispered of another danger. The discovery of the Higgs boson in 2012 confirmed that particles gain their mass from an invisible field stretched across space-time. But calculations suggested that this field may not be truly stable. Instead, it might sit in a false vacuum, a state of apparent stability destined to collapse into something lower. If so, a bubble of true vacuum could someday appear, spreading outward at the speed of light. Inside, the laws of physics would be rewritten. Matter would dissolve. Atoms, stars, galaxies, and life would cease in an instant. This is collapse at its most terrifying, not the creative fall of stars into elements, but the annihilation of reality itself. There would be no warning, no shelter, no survival. The same process that gave particles mass could one day take it away. Escalation deepened further in the multiverse hypothesis, born of inflationary cosmology. If inflation occurred in the first instant of time, expanding space-time faster than light, then collapse was not singular. In different regions, inflation may have ended at different times. Each collapse of the inflated field could have spawned a separate universe, sealed away by horizons. Our cosmos might be only one bubble among countless others, each born from collapse, each unreachable. The very laws of physics, gravity, electromagnetism, the masses of particles, may be the outcome of that collapse. Arbitrary in the landscape of infinite possibilities, collapse, then, is not only universal but plural, an endless scattering of beginnings. But this vision raised another terror. If universes collapse into existence, they may collapse out of it as well. The multiverse might not be an endless birth, but an endless cycle of births and deaths, where collapse is both womb and grave. Even black holes sharpened the unease. They were once thought to be simple, singularities hidden behind horizons, collapse without return. But Hawking's work revealed that black holes radiate, and in time they evaporate. If they vanish, what happens to the information they consume? Does collapse erase the record of existence, or is it preserved in ways beyond our comprehension? This information paradox remains one of physics' deepest wounds. Collapse, in its ultimate form, threatens the very principles of conservation and predictability. As these questions multiplied, collapse revealed itself not as a closed chapter, but as a looming destiny. If the Higgs vacuum is unstable, then collapse waits in silence. If dark energy evolves, collapse may return as a big crunch, a universe folding back upon itself. If expansion continues, collapse may fade into irrelevance, leaving stars and galaxies isolated in eternal emptiness. The escalation is existential. Collapse is no longer just a process that shaped the past. It is the potential fate of the present. The laws of physics themselves are impermanent, subject to collapse into other forms. The fabric of spacetime may not be final, and so the dread deepens. For collapse has become not only a scientific principle, but a philosophical abyss. If collapse is the origin of everything, then it may also be the end of everything. If collapse made us, collapse may unmake us. The same instability that seeded galaxies may carry within it the guarantee of destruction. Yet there is beauty in this terror. Collapse, whether past or future, connects all scales of existence. Quantum fluctuations collapsed into galaxies. Stars collapsed into elements. Black holes collapse matter into silence. And perhaps the universe itself collapsed out of nothing. Creation and annihilation, meaning and fragility, are bound together in collapse. It is not only a mechanism of physics, it is the condition of existence. The mystery deepens not because collapse is rare, but because it is everywhere. And if collapse lies not only behind us, but before us, then the story of the universe is not stability, but constant falling. Creation, destruction, and the unknown all meet in the same motion. The collapse that created everything we know, and may, one day, take it all away. As collapse deepened into paradox, physicists turned to theory. For the collapse that birthed the cosmos could not be explained by observation alone. It required mathematics stretched to its edge, speculation anchored in reason, and imaginations sharpened by the weight of evidence. What emerged was not one story, but many. Each theory offered a vision of collapse as origin, as threat, as eternal rhythm. None yet complete, each a fragment of truth. The first and simplest was the cosmological constant, first introduced by Einstein in 1917. He imagined it as a kind of tension woven into space, resisting gravity to hold the universe steady. When, Expansion was later discovered. He abandoned it, calling it his greatest blunder, yet the constant returned. Today, it is the leading candidate for dark energy, the driver of cosmic acceleration. If true, then collapse itself is frozen, a memory etched into the structure of spacetime, now inverted into expansion. The constant implies that collapse created the universe, but will never return. Still, the mystery lingers. Why does it have the value it does? Why is the energy of the vacuum not vastly larger, as quantum theory predicts? Here, collapse is not denied, but trapped within the silence of numbers. Another vision is quintessence. Unlike the rigid cosmological constant, quintessence imagines a dynamic field rolling slowly down an energy slope. Collapse, in this story, is not finished. The vacuum may shift again. Its energy may wane, altering the expansion of the universe. In some futures, collapse could reverse acceleration, bringing the cosmos back toward a big crunch. In others, quintessence may accelerate without end, tearing galaxies, stars, and atoms apart in a big rip. Collapse here is a living force, shaping futures yet unwritten. The possibility of false vacuum decay is more catastrophic. In this scenario, our universe is perched precariously in a metastable state, like a ball balanced in a shallow hollow on a hill. A deeper hollow exists, a lower energy vacuum where the laws of physics are different. If collapse into that true vacuum were to begin, it would spread at light speed, rewriting reality as it went. Protons might dissolve, atoms unravel, chemistry end. Collapse here is not gentle creation, but instant erasure. Strangely, this possibility is consistent with what we know of the Higgs boson. The particle that gave structure to matter may also be the harbinger of collapse yet to come. Beyond these immediate visions, supersymmetry offers another layer. It proposes that every particle has a hidden partner, unseen because they are heavier. In such a framework, collapses of quantum fields may balance one another, cancelling infinities that now plague vacuum calculations. Supersymmetry could stabilize the Higgs field, preventing catastrophic collapse. It could also unify the forces of nature, showing that the collapse of symmetry in the early universe was not arbitrary, but part of a deeper order. Yet despite decades of searching, supersymmetric particles remain hidden. Collapse here becomes a question of absence. Is supersymmetry real, or is nature more fragile than hoped? From supersymmetry, the path leads to string theory. In this vision, particles are not points but vibrating strings, their harmonies creating matter and forces. Collapse, in string theory, takes a new meaning. Vast landscapes of possible vacua exist, each a different configuration of extra dimensions and vibrating strings. Our universe is one such vacuum, one collapse among countless possibilities. The Big Bang may have been a transition from one string vacuum to another, a collapse within a higher dimensional sea. If so, collapse is not only the beginning of our universe, but the mechanism by which universes multiply. Even deeper is the holographic principle. Here, collapse is not destruction but encoding. Information about everything that falls into a region, stars, galaxies, even universes, may be stored on the boundary of space-time itself. If this principle is true, then collapse never truly erases. Instead, it transforms reality into patterns on cosmic horizons, like writing on the surface of a sphere. Collapse here is paradoxical. It consumes, yet preserves. Other theories turn collapse into cycles. Loop quantum cosmology suggests that the Big Bang was not a singular beginning, but a bounce. A prior universe collapsed inward, but quantum effects resisted infinite density, turning collapse into expansion. In this view, collapse and creation are inseparable, each following the other. The cosmos breathes, universes rise and fall, collapse, and rebirth in endless rhythm. The cyclic universe carries similar echoes. Instead of one beginning, the cosmos may pass through infinite phases of expansion and collapse. Galaxies form, stars burn, entropy spreads, until collapse gathers it all again, condensing into a new explosion. Each cycle erases, yet preserves. Collapse here is not an anomaly, but eternity itself. Speculations multiply because collapse resists simplicity. It is creative, destructive, final, and eternal. It explains the diversity of matter, yet threatens the annihilation of all. It may never return, or it may be inevitable. Every theory frames collapse as both origin and destiny, and beneath all lies the philosophical reflection. Why should symmetry collapse? Why should perfection break? Why is reality woven from instability? Perhaps collapse is not flaw, but essence, the way existence becomes possible. For if symmetry held, there would be nothing. If fields never fell, particles would have no mass. If stars never collapsed, no elements would exist. If universes never collapsed, no space, no time, no thought could arise. Collapse, then, is not failure. It is the price of being. Every theory, from cosmological constants to string landscapes, attempts to capture that truth in equations. Yet, beyond the mathematics remains the same haunting paradox. Collapse destroys, but only by destruction does creation appear. The collapse that shaped the cosmos cannot be rewound. No human eye can return to the instant when symmetry shattered, when the vacuum fell, when space itself surged into being. Yet science does not yield to impossibility. Instead, it builds. Tools, vast, precise, fragile instruments designed to catch the faint echoes of collapse still reverberating through reality. Across mountains, beneath oceans, in the emptiness of orbit, and deep inside particle colliders, humanity has fashioned ways to study collapse not as myth, but as measurable truth. The most powerful among them are particle accelerators. The Large Hadron Collider at CERN smashes protons together at near-light speed, recreating energies that flickered in the universe's first trillionths of a second. In 2012, it revealed the Higgs boson, a particle born from a collapsed field that grants mass to matter. Yet the Higgs is more than discovery, it is question. Its mass, delicately balanced, suggests our vacuum may not be stable. By probing Higgs interactions, the LHC tests whether the universe rests on solid ground or perches precariously above collapse. Planned upgrades will push further, reaching higher luminosities, more collisions, sharper glimpses into the fragile fabric of spacetime. Elsewhere, subtler experiments study collapse's fingerprint on the vacuum itself. Precision Casimir effect measurements place metal plates nanometers apart, detecting the faint pull of quantum fluctuations. These whispers reveal that emptiness is not empty, that collapse of fields fills the void with pressure. Each refinement deepens the map of vacuum energy, testing whether collapse hides in values just beyond detection. But collapse is not only written in the small, it is inscribed across the sky. Telescopes survey galaxies, searching for signs of cosmic acceleration, the after effect of collapse at the largest scales. The The Vera C. Rubin Observatory, rising in Chile, will track billions of galaxies, mapping how their clustering evolves. Its nightly sky surveys will probe whether dark energy, the frozen echo of collapse, is constant or shifting. If dynamic, it may reveal whether collapse has not ended, but continues, reshaping the cosmos in real time. The Euclid mission, launched by the European Space Agency, extends this work, charting the geometry of spacetime itself. By mapping gravitational lensing, the way galaxies distort light behind them, Euclid unveils the scaffolding of matter and dark energy. Its data may confirm whether collapse's legacy is truly a cosmological constant or whether subtler fields still roll beneath the horizon. Soon, NASA's Nancy Grace Roman Space Telescope will join, designed to measure cosmic expansion with exquisite precision. Roman's surveys of supernova and galactic structure may distinguish between static and dynamic collapse models. Together, Rubin, Euclid, and Roman form a triad of eyes, racing to chart collapse before the universe drifts beyond our vision. Deeper still, scientists study collapse, imprinted on the cosmic microwave background, the oldest light in existence. Missions like COBE, WMAP, and Planck have mapped this ancient afterglow with stunning clarity, revealing faint ripples seeded by collapse in the infant universe. Now, future projects like BIRD and CMBs aim to push further, detecting polarization patterns that may confirm inflation, the brief, colossal collapse of a field that inflated spacetime faster than light. If found, these signatures would not only prove inflation, but reveal the quantum collapse that sculpted every galaxy in parallel. Gravitational waves have opened a new window. First detected by LIGO in 2015, these ripples in spacetime recorded the collapse of black holes into one another. Yet gravitational waves may carry more than astrophysical stories. Some models predict the primordial collapse during symmetry breaking. During inflation, left behind a background of gravitational echoes. Space-based observatories like LISA will extend detection into lower frequencies, perhaps capturing the faint tremors of collapse at the dawn of time. Even in laboratories, collapse is simulated in miniature. Ultra-cold atoms are shaped into Bose-Einstein condensates, where scientists mimic black hole horizons and detect faint radiation akin to Hawking's predictions. These analog systems, though far from cosmic in scale, confirm that collapse can be modeled, its principles tested, its paradoxes tamed into experiment. Supercomputers add another dimension, simulating universes where collapse varies. In one model, the Higgs vacuum is stable. In another, it collapses. In one, inflation ignites. In another, it fails. By comparing simulations to the structures mapped by telescopes, physicists test which collapses birthed our universe and which belong only to imagination. Dark matter experiments also tie into collapse. If supersymmetry is real, then new particles may emerge, relics of collapsed symmetries from the early universe. Detectors like Xenant and LUX-Zeppelin, buried deep underground, search for faint signals of dark matter scattering. Each silence tightens constraints, each hint whispers of collapse's deeper layers. Yet beyond machines and data lies urgency, for collapse defines both beginning and potential end. If the Higgs field is unstable, collapse may return. If dark energy shifts, collapse may accelerate. If false vacuum decay waits, collapse may strike without warning. Each instrument humanity builds is not only a probe into past creation, but a safeguard against future erasure. A way of asking whether the ground beneath reality will hold. Still, the ocean of collapse resists capture. Experiments refine, telescopes expand, theories adjust, but collapse remains elusive. Perhaps it cannot be isolated, only approached. Perhaps it is too deeply woven into existence to bound to the nature of time. Yet the pursuit continues, relentless. For to measure collapse is to measure origin, destiny, and the balance between fragility and creation in the great halls of CERN, in the dark caverns of underground detectors, on mountaintops where telescopes gaze at fading light, and in the silent hum of satellites drifting beyond Earth, humanity's instruments wait. They listen for collapse not as end, but as truth. For in collapse lies the secret of how everything began and how everything may yet end. Collapse, a word that carries the weight of endings. Stars collapsing into darkness, buildings falling to ruin, lives folding under time. Yet in the cosmos, collapse is not only destruction, it is the rhythm of renewal, the hidden architect of everything we know. To reflect upon collapse is to see creation not as permanence, but as transformation, the fragile balance of breaking and becoming. The stars themselves bear witness within their cores. Gravity and fusion wage eternal war. When fusion falters, collapse takes command. A star implodes, and in that violence the elements of existence are born. Carbon, oxygen, iron, gold. The death of a star becomes the birth of planets, oceans, and living minds. Collapse scatters the dust from which eyes evolve to look back at the sky, asking how it all began. Without collapse, there would be no breath, no thought, no question. Creation depends on ruin. The universe, too, carries collapse at its origin. In the earliest instant, perfect symmetry reigned. No difference between forces, no particles distinct from one another. But perfection is unstable, symmetry shattered, collapsing into difference, into matter and force, into quarks and electrons, into light and gravity. Out of collapse came diversity, structure, and the possibility of life. The cosmos is not a monument to stability. It is a cathedral built from brokenness. And yet, collapse also reminds us of fragility. The Higgs field may be metastable. If so, the vacuum that cradles reality is temporary, destined to collapse into a deeper state. No warning, no escape. In an instant, physics itself would be rewritten and the universe extinguished. The same mechanism that once birthed galaxies may someday erase them. Creation and annihilation are not opposites, but reflections to faces of collapse. Philosophically, this unsettles. Humanity longs for permanence, for foundations that do not break. Yet the cosmos offers no such comfort. Its laws are born from collapse. Its structures are carved from impermanence. To exist is to inhabit a world where stability is illusion, and collapse is truth. And perhaps that is not tragedy, but meaning, for collapse also teaches resilience. Life itself is collapse harnessed, cells dying so that organisms grow, forests burning so that ecosystems renew. Human lives mirror this cosmic cycle. Every ending births a beginning. Every collapse reshapes the path forward. Even civilizations, built and broken, reflect the same law. Collapse defines not just stars and atoms, but the arc of human story. At the largest scales, collapse defines destiny. Will the universe expand forever, stars fading into silence? Will dark energy shift, collapsing galaxies into a final fire? Will false vacuum decay erase all in a single sweep? The future is uncertain, written in equations not yet solved. But collapse, in whatever form it takes, is inevitable. This is not cause for despair. It is a reminder that nothing is wasted. Even in endings, something new is made. Perhaps then, collapse is not the enemy of existence, but its essence. Without it, no star could shine, no element could form, no universe could expand. Collapse is the hidden generosity of the cosmos, the paradox that destruction gives rise to life. It is the reminder that fragility is not weakness, but foundation, that to break is to allow creation. In this light, collapse becomes almost sacred, not as doom, but as passage, not as ruin, but as transformation. The universe is a vast archive of collapses, each one giving birth to what follows, the collapse of symmetry birthing forces, the collapse of stars birthing elements, the collapse of matter into galaxies, the collapse of time into memory. Humanity stands within this chain, not separate but part of it, shaped by collapse, carried by its tide. And when the universe itself meets its final collapse, whatever form it takes, perhaps it will not be an ending at all. Perhaps it will be the seed of something new, another cosmos, another cycle, another chance for matter to think, for light to shine, for meaning to rise from nothing. For collapse is not only the past, but the promise that creation is never finished. So the story closes where it began. Collapse, a single word, heavy with ruin, luminous with possibility. It created everything we know, galaxies, stars, oceans, thoughts. It may yet take everything away. But in its paradox lies beauty, that fragility and impermanence are not failures, but the very conditions of existence. The final image is this: the universe as a cathedral of ruins, built from collapses, illuminated by the fires of what once fell. Within its halls, humanity walks, fragile yet aware, knowing that collapse shaped the beginning, sustains the present, and will one day write the end. And perhaps that knowledge is enough, for in collapse lies not despair, but wonder, the reminder that to exist at all is to stand in the echo of creation's first fall.